Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Hey, step on inside here, and this is actually integrated Math 1 based material. The last month or so, what I've been doing with my kiddos is just introduction to algebraic concepts. Combining like terms, simplifying expressions by combining like terms and using the distributive property, solving linear equations, two-step equations, multi-step equations if there's a little simplification to do. Let's see what came next. Solving literal equations after that. And then a couple things with word problems. Some where you translate algebraic, all of them are translating words into algebraic expressions, but some into equations and then solving them thereafter. I have 10 questions for us to just cover, 2 per skill. And I'll write out what those skills are when we go ahead and do them. Let's go and get started and take a look at some of them, shall we? Skill number 1 here is the simplifying expressions stuff. It says right there when it says simplify. Simplifying expressions. You may be combining like terms, you may be using the distributive property. Now what you're looking at here is in essence a practice quiz for my kiddo. Sorry for the handwriting. It's in essence a practice quiz for my kid, and I just sneezed a little bit ago, so sorry for the sniffles. My kiddos do skills-based material here where they are doing 2 questions of skill and saying, can you master them? Can you do those ones? And so they'll change every time. The kinds of questions you see will be the same, but the idea what happens will always change no matter what. Sometimes they have x squared, sometimes they have y, sometimes you distribute here, and whatever. So anyway, here are the 2 that you get. Let's just talk about what's going on here. All right, number 1, simplifying 2x minus 1 minus 9x plus 4. This means rewrite this thing so that like terms are combined, so that you see 2 different x terms right here, and right here. Let's make it just a single x term. You see 2 different constant values right here. Let's make it a single constant value. It's as if, not the same thing, but it's as if I said, hey, do 2 minus 1 minus 9 plus 4. We turn it into a single number, right? And this won't be able to turn into one single number. It'll have to turn into 2 different terms. A variable term, a term with x's in it, and a constant term, a term with numbers in it. And the ideas with x's, 2 times x literally means x plus x, like that. Minus 9x means minus 1, 2, 3, 4, 5, 6, 7, 8, 9 x's. And then the question becomes, how many x's remain from that? You know, and if this isn't how I'm always going to do it, I'm just talking it through. If I do this x minus this x and this x minus this x, I'm left with 7 other x's that are being subtracted from each other. I have 7 x's being subtracted. It would be like that. So what you're actually doing, you might know that 2 minus 9 is also negative 7. Let me just rewrite this right here, where I'm going to rewrite it as 2x minus 9x next to each other. That'll become negative 7x there. And then I have the negative 1 over here, and we're adding 4 to that. And I ask you what's negative 1 plus 4. We should be able to do that. It's like 4 minus 1. It's 3, not negative 5. And that becomes an answer there, negative 7x plus 3. We have simplified this expression. What we've done was made a smaller version, or somewhat cleaner, whatever version of the previous expression that was there, such that even though we don't know what x is, we're not solving for x, even though we don't know what x is, if I substituted any value imaginable for x, anything I want, 0, 5, negative 10, whatever it is, I'll get the same value here as I would here. Let's see if that works. Let's substitute 6. 2 times 6 minus 1 minus 9 times 6 plus 4. Is it equivalent to negative 7 times 6 plus 3? Well, this is 12 minus 1, which is 11, minus 54, which is negative 43, plus 4, which is negative 39. What's negative 42 plus 3? Negative 39. Well, that checks out there. So we wrote an equivalent expression, but we have simplified it in such a way that substituting that in for x, I think, made it a lot easier to do. I think you'd agree on that. And there are other benefits to it as well, and we're going to see them when we start solving equations, I hope. If we simplify, it looks like we might. All right, number 2, simplify this one as well. Now, this uses what's called the distributive property. We are multiplying 3 with parentheses, or we're multiplying 3 by this sum x plus 1, and then we subtract the quantity x minus 7. There are a couple ways we can look at that. I'll try and be kind of quick with them. But the distributive property says that, you know, the idea of multiplying, right? This could be 3 times 2 plus 1, and you can either do 2 plus 1, which is 3, and 3 times 3, which is 9, or you can multiply 3 into 2, multiply 3 into 1, and add that result like this, 3 times 2 plus 3 times 1, which is 6 plus 3, which is 9 still. You get 9 regardless. Now, in 3 times x plus 1, we don't know the value for x. So I cannot, just like here, I can't combine negative 7x with 3. I can't combine x with 1 right here. They have to stay separate. But 3 can still multiply into them somehow and simplify a little bit, which means to us getting rid of the parentheses. There is a benefit to it when I can combine like terms with other things that are also out of parentheses. So I'll multiply the 3 with the x. I get 3 times x, which is 3x. And 3 times 1 is 3, like that. And that's the distribution of the 3 into those two terms. Now, this negative right here, the way I tend to say it in older videos, if you've seen them as well, I can also distribute this negative into these two terms as well. And I'll explain it a second way in a moment. Distributing the negative means change the sign from what it was. This is a positive x. Let's make it a negative x. Let's make this minus 7. Let's make it a positive 7. Subtracting a negative becomes addition. Now, if you have trouble looking at distributing a negative that way, you can also think of it as this is really a negative 1. You know, anytime that you see x, like this x right here, that means 1x. But it's implied that it's a 1 right there. We don't have to say anything about that, so we just leave the 1 away. We just know that x means 1x. Why am I saying that? Because anytime that I take anything, this x minus 7, that means x minus 7 times 1. There's nothing to it having the 1 outside of there. It shouldn't change it. With a minus in front of there, right, if that was a negative 2, we would say distribute negative 2 into these and multiply negative 2 times x and negative 2 times negative 7. So let's pretend like it's a negative 1. What's negative 1 times x? It's negative 1x. What's negative 1 times negative 7? Positive 7. And that's what we have. So you either say distribute the negative into those two terms or distribute a negative 1 into those two terms. To me, it's the same thing, changing the signs of the values. Anyway, now we're at a stage like this other problem right here. It's actually very close to this kind of problem. It's almost like level 2 of the problem here. 3x minus x happens here. And remember, that is 1x. 3x minus 1x, 2x. 3 minus 1 is 2, combined like terms. 3 plus 7 is 10. And notice it's not 3 minus 7. The negative times in with that x right there. And that's what that is here. And again, I can substitute a value. I could try and substitute 15 into here. And I'll get 40 here. And 3 times 16 is 48 minus 15 minus 7. So minus 8, right? Notice how I had to do 15 minus 7 first in there, and that's also 40. Just making it up. Okay, let's look at skill number 2 now. Hopefully that kind of made some sense there. Whoopsie, whoopsie. Skill number 2 will be solving equations. Solving, simplifying expressions, solving equations. So really the way I'm talking about these guys is I'm running these down very, very slowly. I want to make sure that whomever is looking at these things gets it, right? I want to know that they understand what's going on. All right, solving equations. We're trying to figure out, I'll try and go a little faster with these here. What value of x makes the left side equal the right side? And we're not just plugging in number, we're not trying every number in the sun till it works. Hey, let's try 1. That's 4 times 1 plus 6. That's 10. 5 times 1 is 5 minus 9 is negative 4. 10 doesn't equal negative 4. That means x doesn't equal 1. Let's try 2. No, you don't want to do that. For 1, there might be no solution. 2, there might be negative solutions. 3, there might be fraction solutions. 4, the solution might be 160. There's another way to work at it here, and this isn't the easiest kind of problem to do it. That's why, like I said, these problems vary every single time. Sometimes they're two-step equations, sometimes blah, blah, blah. So I can only say the best I can with what we're going to do. Let me start by rewriting this problem right here so I have a little more room. 4x plus 6 equals 5x minus 9. Here's the goal. We want to solve for x, which means we want to see what x becomes, what x equals. Wouldn't it be great if we can do some rearrangements with this equation so that the equation ended up just saying x equals? By rearrangements, I don't mean just moving things around. Maybe I say that out loud, but I mean mathematically move things around. Subtracting numbers to both sides of the equation, adding numbers to both sides. Here's basically what we're going to do. Would you agree that 10 equals 10? I would agree that 10 equals 10, right? If I subtract 4 from 10, I get 6. Does 6 equal 10? No, it doesn't. How come those don't equal each other? Because you subtracted 4 from this side, Mr. Robinson. You can't just do that. You subtract 4 from this side, you'll be good. 6 equals 6, right? It still checks out. Notice that if I do something to this side, I can totally do it, right? We can multiply this by 20 and multiply this by 20, and they still equal each other. I can do anything to one side of the equation as long as I do the same thing to the other side of the equation, and that's totally cool. I literally change the values. I'm manipulating in such a way that I'm seeing different numbers out, but I'm keeping balance in the equations. And the idea for me is going to be, let's make this say x equals. X equals. X equals also means 1x plus 0 equals in a way. So here's the thing. I got 4x's right here, 5x's right here. Now, you can move the x's to either side of the equation. I have a preference, and I'm not going to start with my preference here. one version we could do is say, hey, get x's to the left side of the equation. Just naturally, and when I draw this little line here, it's just going to say, here's separating two sides of the equal sign right now, the barrier of the right side versus the left side. Let's say that, I don't want x's on this side of the equation, so I'm going to subtract 5x from this side. You know what 5x minus 5x is? It's 0x, and 0 times x, which means it's 0. There are no more x's on this side of the equation. I've removed all 5 of them. But my equation is no longer balanced. Now I don't have any, I didn't subtract 5x on this side, and I got to do that here. If I subtract 5x on one side, I can subtract 5x on the other side, and all's good. And 4x minus 5x is not 0x as well. That is negative 1x. Negative 1x, you can also just say negative x like that. Now this says negative x plus 6. I didn't do anything to that 6 yet. And then I have a negative 9 over here. Don't forget the negative, and you'd be good there. That's pretty good. Now I'm trying to make this say x equals, and I'm on my way to doing that. Think of this now in this way. It makes it a little bit easier. I'm taking some unknown number, multiplying it by negative 1. And then I add 6 to it. And the value I get is negative 9. And then I ask what that value is, right? It sounds like there are 2 things away from me figuring out what that number is. First, that unknown number did multiply by negative 1, and then it added 6. The last thing we did was add 6 to get negative 9. So I ask you, hey guys, what number do you add 6 to get negative 9? Or not really what that number is, but how do you find out what it is? Besides just saying it out loud. If something plus 6 equals negative 9, then negative 9 minus 6 equals that number, right? So we can kind of do that same thing right here. If I subtract 6 from both sides like that, subtracting 6 from here to get the value, subtracting 6 here because of balance, right? If I do that here, then suddenly I don't have any 6 over here anymore. It's just this negative 1x plus 0, but negative 1x equals. And negative 9 minus 6 is negative 15. That was the number we're coming up with. I said I'd go fast with this, and I'm clearly not, but I'll go fast with the next problem. Some number times negative 1 equals negative 15, or the opposite of a number. You can even write negative x equals negative 15. Hey guys, I want to know what x is, right? You look at this. Hey guys, what's x? If negative x is negative 15, what do you think positive x is? It's positive 15, right? In a mathematical sense, we can work backwards from what we just did before. If something times negative 1 equals negative 15, how do you find that number? I multiply a number by negative 1 to get negative 15. If the negative thing sounds weird, try this. Some number times 2 equals 8. Don't just tell me what the number is, but how do you get that number? Something times 2 equals 8, so 8 divided by 2 is that number. You do the opposite of what's affecting your numbers, basically, and you've kind of noticed it right here. I had a positive 5x. Let's subtract 5x. As far as moving x terms over, that's kind of a strategy that we'd want to use to get an x by itself on one side of the equation, right? Something's multiplying by x now. Let's divide it by that number that's multiplying by x. Let's divide by negative 1. You know what negative 1 divided by negative 1 is? It's positive 1. And you know what that gives us? A positive 1x. We better write it as x. You'll see me do that cancel thing time to time. It just goes to show that that number doesn't appear anymore. It is now a 1x plus 0, but we don't write 1x plus 0. We just write x equals. And a negative divided by negative, once again, is a positive. Negative 15 divided by negative 1 is positive 15. And that is the value. And yeah, I spoke in that in a long way, and that was only one version of what I could have done. I will show you the other one a lot faster. But if you ever wanted to know if you were right, you could double check and see if 15 does work in here, right? We need the left side to equal the right side. 4 times 15, that's 60, plus 6. Does that equal 5 times 15? That's 75, minus 9. 60 plus 6 is 66. 75 minus 9 is 66. Yeah, it all checks out. That's the only number that works here. There's no other value that works, only 15. And we did some approach to work that out, if you know what I mean. We did some algebra. We did some algebra, moving terms to other sides of this equal sign right here to make that happen. Now here's how I would have done this problem. I would have done the exact opposite here. You notice how we had to divide by negative 1 at the very end to make that work because my x term was negative. People tend to kind of mess up that part in a lot of different ways. Sometimes people forget this negative 9 all alone. Sometimes they don't know what to do when it's just a negative 1x or a negative x. I like to try and keep my x terms positive. If the last thing I got to do is divide, I'm going to want to divide by a positive number. It's a preference of mine always, and even if you want x on the left side of the equation, we can switch it over time. That's fine. So instead of subtracting 5x from both sides, I know that 5 minus 4 would give me a positive number, so maybe I subtract 4x from both sides this time instead. 5x minus 4x is 1x. I was going for a 1x as an answer anyway. I could just write x, right? And if you want to do these all in one step, you could say, okay, if I'm moving x's to the right side of the equation, let's move our constant values to the left side of the equation. I want to know what x equals. I don't want this to say x minus 9, dot, dot, dot. I want it to say x equals, dot, dot, dot. So this negative 9 is all like, hey, you're in the way of my x. Let's do the opposite. If I have negative 9 here and I want to turn this into 0, I should add 9 to it. Make it 9 larger. X minus 9. Some number minus 9 is 6. I want to know what it is. I could just write it right here. Negative 9 plus 9 is 0, and 6 plus 9 is 15. We get x equals 15. And maybe you don't want to write it that way, and you can write it that way, and you're totally good. That still took me, well, that took me 2 steps instead of 3. Here I had to subtract 5x, then subtract 6, then divide by negative 1. Here I had to subtract 4x and then add 9, and I was done because it was 1x equals. Maybe I was lucky, but I did keep the x terms positive, and that's something that I mostly prefer doing there. Okay, there's number 1 there. Number 2, let's go and look at this here. Now x is buried inside of a parentheses, right? If I multiply 8 by the difference of some unknown number and 1, and then I add 2 to that result, then I get 20. What is my number is the question. So, again, I'm going to go a lot faster on this problem here, but the general idea is that, x is totally buried inside parentheses and such. Let's get x as much out of it as possible. And I can't do negative 1 plus 2 right here because negative 1 is being multiplied by 8 the same way that x is. But if I distribute that 8 into x and negative 1, like we did on the first skill, you get 8 times x, and then 8 times negative 1, you get 8x minus 8. Plus 2 equals 20. So what I'm doing is I'm simplifying the left side of my equation. The right side's fully simplified. It's just a 20. I have nothing else I can do with it. But the left side needs some simplification. And it's not really always required. There are other ways you can go about it, but this is definitely most recommended for just a plethora of reasons. Just this great multitude. I can totally see that way. And you know what? To be honest, if you don't mind, I want to change this problem. I made an ouchie. I made an oof. There was something that I think I wanted to do. I can't see in full what it was that I wanted. You know what? I'm not going to change the problem. Let's keep it as it is. Mr. Robinson didn't... Can I change the problem? I want to speak to not having a fraction. See, this is going to have a fraction answer if so. I'm not going to change the problem. I'm not going to change the problem. I'm going to keep it. We're going to have a fraction answer, and it goes to one of those things you couldn't just plug in any number in the sun, under the sun. I messed up. That's okay. Okay, there was something else I thought I wanted to do when I first made the problem. That's totally fine. But let's simplify this left side of this equation right here. I have a left expression right here that is unsimplified because negative 8 plus 2 isn't fully what I want it to be yet. If I take a number, multiply it by 8, then subtract 8, then add 2, you're like, why don't you just say subtract 6? Negative 8 plus 2 is 6, right? Why are you wasting my time saying those other instructions? What if I said 1 plus 3 minus 7 plus 4 plus 0? You're like, just tell me what that number results to, and then we'll get going. Some number times 8 minus 6 equals 20. I want to know what that number is. Plus 6 is the last thing that occurs there, so let's go ahead and add 6 to figure out what that is. You always kind of do opposite of what's affecting x on that side of the equation that you're trying to get x by itself on. 6 is being subtracted. Let's add it. That gets you 0. So we have 8x equals and 26. So 8 times, what number times 8 equals 26? It's not, see, that's not a clean number. It's a Robinson goof, little ouchie. That's not to say fractions can't be answers. And by the way, the answer is not no solution. It is a fraction. And let's leave it as a fraction, even though you could say it as a decimal as well. I think the actual decimal is 3.25. But we'll just use an improper fraction and we'll reduce it. That's a common practice in math. And let's accept the idea that they're possible. So that's why I was thinking, maybe I should keep it. How do you find out what number times 8 is 26? You divide 26 by 8 to figure it out. Right? If 8 times some number is 26, then 26 divided by 8 is that number. 8 divided by 8 is 1. We get 1x equals 26 over 8. Now I will reduce this fraction that involves dividing top and bottom by a common value, and such as 2. I can divide 26 by 2 and I get 13. Divide 8 by 2 and I get 4. 13 fourths, otherwise known as 3 1/4, otherwise known as 3.25. I'll tell you what, unless we're talking about a word problem or we're trying to graph it, this is really it's really the best answer. It's the one, it's accepted. Don't think of improper as bad. It just means you have more on your top than you do out of your whole. That sounds weird to have, right? How can you have 13 quarters of something? Of quarters, I guess. But it's something you could also compute numbers with. It's the most accepted answer. You're going to see it most often. And yes, reduced as well. Reducing the fraction, dividing by 2 on top and bottom there. Okay, you know what? We had a fraction. That's okay. We'll deal with it. We have fractions all over the place sometimes. Some of these are fractions as well. Let's take a look at this one. Number 1a. Oh, skill number 3. These are called literal equations. What we're going to do on these ones here is we are solving for the variable asked for. Now, for whatever reason, students have more trouble with this than I feel they should. Literal equations are a lot like the equations above. If you feel like you know what you're doing with these things, these should be a cinch. The only difference is that your answer might not have just a single number. It might have letters. And the literalness of it is like, hey, guys, what is A plus B? It's not C, it's just A plus B. A and B don't combine, so you just leave it as A plus B. So when you ask what is A plus B, just say yes, it is. Now, are we going to do A plus B here? I don't think so, but we're going to do something close to it. It says solve A equals B minus X for X, meaning I want this to say X equals. Now, literal equations have their usage. We talk about slope-intercept form, things like that, y equals mx plus b, getting y by itself. In different other formulas, isolating that one thing says that's how you get that particular part by itself. So they have their uses here. And there are, again, two ways I can do this problem, a lot like this number 1 and skill number 2. Problem 1 and skill number 2. Solving for x. Hey, let's get x on its own side of the equation. Let's subtract b from both sides because it's a positive b that's adding with the negative x. B minus b is 0, but a minus b don't combine the same way that x plus y would not combine. This now says a minus b equals negative x. Now, we would divide everything by negative 1 the same way that you saw before, right? That is technically a negative 1x equals, and you have to know that. And what we would generally want to do, you can say this in one of two ways. You can say let's divide everything by negative 1, but then literally divide everything by negative 1 here. Dividing by a negative 1, as you saw before, changes its sign. It doesn't change the value outside of its sign. So dividing everything by negative 1 means we divide a by negative 1, change its sign. Divide b by negative 1, change its sign. So you get x equals, and yes, I'm writing it on the left side here, negative a plus b, changing their signs. That's one way you can write it. You can also write it as b minus a, of course, changing their order. Now, that might have been a confusing problem for you. Maybe not because the letters, maybe the negative 1. You're like, Mr. Robinson, I was with you until you did the negative 1 thing. What's going on there? Well, that's part of the recommendations where I say whatever variable you're solving for, try and keep your variable term positive. So let's go back to that problem one more time. Let's go back to the well, and let's make our variable term positive first. X is negative on this side of the equation. What if I added x to both sides of the equation? What if I did plus x right here, made it become 0, and then plus x over here on the left side of the equation, and now I have a positive x and a positive a, like that. Boom, x is positive. It's on the other side of the equation, but it's positive now, right? 2 equals 5 minus 3, but 3 plus 2 also equals 5. You notice how that negative 3 turns positive over there. Now if I subtract a from both sides right here, then you notice now you get x equals b minus a, and that's kind of the other way I was writing it there. So there's a version of a literal equation right there, and that's solving for the variable that's requested. And notice they had to give you which one it was solved for. Technically, A was solved for right here in the beginning of the problem. So if it said solve for A, you go, ta-da, I'm done. If it said solve for B, I would add x to both sides, and that would be it. It's just as literal as that. Just it doesn't clean up. That's okay. All right, let's look at number 2 here. Solve P equals 2w plus 2l for w. This means, this is like a perimeter thing. Perimeter equals 2 widths plus 2 lengths. Width plus length, and you get the whole perimeter right there. It says solve for w, so basically, what does the width represent in your thing? Somewhere I think perimeter's in the answer, right? And we're going to go ahead and do that. So let me write this one more time here. P equals 2w plus 2l. I may need the room. We need to get w by itself. And what we've seen a couple times right here is the width is being multiplied by 2, and then it's being added to 2 lengths, and voila, you get the perimeter. So how do we get the width from that? Well, 2 lengths was added to get the perimeter at the very end, so in order to figure out those widths, let's start by subtracting the 2 lengths. They are being added, let's subtract, do the opposite. L's can't combine with P's at all, no matter how many L's and how many P's there are. So we end up getting P minus 2L equals 2w. Notice how w has always kind of been positive. That's nice. And then we can divide everything by 2 right here. Something's multiplied by 2. See, you want to treat p minus 2l. We might not know what that number is. It might not combine as something, but it's treated as one quantity. It's one number right there. This p, the perimeter subtracts from 2 lengths. It's some number. And then if we divide everything by 2, then that whole number gets divided by 2 like that. Now, you notice how I'm going to do 2 divided by 2, which is 1. And you might think, hey, let's do 2 divided by 2 here. Be careful with that. You can in some instance. I'll show you what it is. But for now, we'll just leave it like this. W equals P minus 2L over 2. Now, there are a couple reasons you can't do this whole, hey, cancel these out. Number 1 is 2 divided by 2 does not equal 0, it equals 1. So when canceling those out, it's not like they would just go away, right? It's still 1, so I guess it's 1L, so there's that. But number 2, P is also being divided by 2. It's not just L. If you wanted to, you could separate this into 2 separate terms. P over 2 minus 2L over 2, just like I did with negative 1, right? They could both divide, where is it? I might have erased it. But they could both divide by negative 1 in one of the other questions. Oh, right here. They can both divide by negative 1 right here, or you can write it as like all divided by negative 1, I think I said. We could separate and divide them both by 2. This way, this 2 divided by this 2, yeah, they go away in that they become 1, but you're still left with this minus L right here. So that's P over 2 minus L. So what did we say in this answer here? The width of, let's say it was a rectangle, because rectangle does this. The width of a rectangle is either you take the perimeter, subtract double the length, and then divide all that by 2. That sounds like a lot. Or take the perimeter, divide it by 2, and then subtract one of your lengths. That's how you get the width of any rectangle. Interesting. Didn't really think about it that way. All right, 2 more skills. Skill number 4, it's word problems to translate algebraic expressions. We're actually not going to solve these ones here. Skill number 5, we will. This video went on a lot longer than I expected. I was thinking of doing this one of 2 ways. In fact, I will do a second one that's just very cut and dry, very fast. If that's cool. I think I'm going to do that because this is going to go beyond a half hour. All right, translate the following algebraic expression. Translate the following sentences, phrases into mathematical expressions in equations or inequalities. Mr. Robinson, Y is at least twice your age, X. We want to create kind of an equation out of this, right? We want to compare my age to your age. I'm at least twice your age. Now, let's first start with this. I'm going to start by writing Y equals X. Is it true that my age, Y, is equal to your age, X? No. But we can start off with this. Let's say the idea was Mr. Robinson's age is your age. It would be Y equals X. It is a comparison of 2 things, therefore it is an equation. The word is makes that equal sign happen. And an expression for my age is right here with Y. And on this side, we would at least have your age right there, which is X. Now, don't worry, I'll talk about that at least portion right here, but let's talk about the twice your age portion. What is an expression for twice your age? Think about it. If you're 10 years old, I'm not 20, but if you're 10 years old, what is twice your age? You take 10 and you multiply it by 2. 2 times your age. Well, what is your age in this case? We don't know what your age is. X, right? What's twice that age? You take that X and multiply it by 2. So an expression for twice your age would be 2X, like that. This would be an equation for Mr. Robinson's age is twice your age. And that's what that would be. Okay? But it says at least twice your age. Is at least twice your age. That means you could be 10 years old because whatever age you are, I may be double that age or I may be more, which I am. I'm not 20. So how do you write is at least? We don't have an equal sign anymore. I could be twice your age, but I also could be more. So how do you write that? There's something called an inequality. There are inequalities that are like greater than, less than, greater than or equal to, less than or equal to. And when I say greater than, etc., I'm talking about the left being greater than the right, or the left being less than or equal to the left, things like that. If I'm at least twice your age, then I am your age or greater than. So that is greater than or equal to, like this. Y is greater than or equal to 2X. Mr. Robinson is at least twice your age. And that is the equation, the inequality that we would write from that one. Okay, second one right here. Joe bought X pounds of potatoes. So we're looking at this table over here, Pearlie's produce. Joe bought, you know what? I'm not going to do a second video with this. You can fast forward and watch them. We're there. Joe bought X pounds of potatoes, Y pounds of onions, and Z ears of corn. Z ears of corn. Sorry. Write an expression for how much money he spent at Pearlie's produce. Keep in mind, we won't know exactly how much money he spent at Pearlie's produce, but let's make up numbers. The reason I keep saying this is to help you understand how to come up with these things on your own for yourself, or understand why these terms say what they are, because students mess this up all the time. All the time. Literally on the fly, I can anticipate what a student will say before they say it. Maybe they'll say the right thing, but I know when they'll say the wrong thing and what that wrong thing is going to be. let's say for a moment Joe bought, and I'm not going to get the actual number for you, but Joe bought 5 pounds of potatoes, 10 pounds of onions, and 20 ears of corn. Okay. How much money did Joe spend? Each potato potatoes cost 45 cents per pound. If you bought 5 pounds of potatoes, you take 45 cents per potato, or per pound of potatoes, and multiply by the 5 potatoes. That gives you yay money. That's actually $2.25. Maybe I can do this on my own, but $2.25. 10 pounds of onions, you pay 96 cents per pound. 10 pounds, you take that 0.96 and you multiply by 10. That's actually 960. Hey, I can do this in my head. Remember, I made these up. I'm going to replace these in a moment. 20 ears of corn. That's a lot of corn. 75 cents each per ear. So multiply 75 cents per ear of corn by the number of ears of corn that you buy, 20. And that is $15. So, I could do that. So what's 220? No, I'm sorry, 225. 225 plus 960 plus 15, I think I said, plus $15 right there. That is $11.85. That is $26.85. Joe spent $26.85 of Brothers Produce. What we did here, what I did here was I used real numbers. I didn't care what the numbers were. I was just saying. But what I did here was I showed you how this expression will be laid out. You are going to multiply the price per pound of potatoes. You're going to take that number and you're going to multiply by the number of pounds of potatoes that you bought. We don't know how many pounds he bought. We called it X. You're going to take 0.45 and multiply it by X. Then you're going to take the amount that he spent how many pounds per onion, 96 cents, and you are going to multiply by the Y pounds of onions that he bought. And then you will take the 75 cents you buy per ear of corn, you spend per ear of corn, and you multiply it by the Z ears of corn that he bought. Each individual term shows how much he spent on potatoes, on onions, and on corn. On potatoes, on onions, and on corn. And when you add them up, you get a total. Now, we didn't have actual numbers here, so I'm going to erase them. But here is the expression. It's nothing equals or whatever. I mean, unless you're actually computing it and they tell you and they say solve for this. But this is an expression for how much he spent. You add those results together. This is a dollar amount plus a dollar amount plus a dollar amount. And that's what they total to. That's the idea of those things. There's a lot more different kinds of problems you could have, obviously. This is just among one of them. But that's what I wanted to work with there and give you the idea. This thing multiplied does that. And I didn't dispel a lot of the issues that people do have with those kinds of things. Because, like, if I just ask you, what does 0.69y represent? A lot of people will say, 96 cents onions, right? It's not. It's not that. It's how much did you spend, right? How much did Joe spend when I said 10 onions? He spent 960. 0.96. 96 cent onions doesn't equal 960, right? It's still multiplying by y, the number of pounds of onions that he bought. So that's the thing that people tend to mess up on a little bit. All right, last skill here. It still has to do with algebraic things, but we're solving word problems in a way here. Solve word problems. And I'll tell you what, eventually we're going to run into old videos, or I'll make new videos where we do something called systems of equations, where I feel more comfortable talking about these problems that way. But I'll still work these out in a way that I hope is beneficial to you. And let's actually solve after we set them up. All right, Henry is saving money to buy a new pair of glasses that cost $225. He has $45 saved, and each week he adds $30 to his savings. How long will it take him to save enough for the sunglasses? Okay, here's the thing. There's something that we don't know about this problem. I mean, there are a lot of things we don't know. We don't know how old Henry is and things like that, but there are only things that are pertinent to the problem that we need to figure out. We know how much the glasses cost. We know how much he saved. We know how much he adds per week. So something is going to add up to $225. All of his money that he has, that's $255. All the money that Henry adds, invests, saves, is going to add up to $225. Well, he has $45, and then he adds $30. Does that equal $225? No, that equals $75, because he adds $30 the next week, and another $30 the next week, to $60 and $90 and $120 and $150. Right? It keeps going. How many weeks will it take for him to do it is the part we don't know. The unknown, how long, how many weeks. Let's put a W for number of weeks, or an X or something like that. We got to still solve this thing. I mean, we're going to set it up. And listen, if you add enough times, you can probably just land on it in a table. That's not the goal. The goal is to create an equation that works this thing out in such a way that you could solve it on your own all the time. So we're not taking forever on the table. We don't, it's not a fraction, whatever else. How many weeks? Well, we just talked about before with like ears of corn, stuff like that. 75 cents per ear of corn. What if you multiply by the number of ears of corn? What if you save $30 per week and multiply by the number of weeks? See, if W is 10, you take 10 weeks, $30 per week. That's $300 saved. In addition to the 45 he already started off with. This was an initial saved amount. It's not affected by the number of weeks. No matter how many weeks he puts in $30 over and over again, he'll still have that 45 just sitting in there, right? Even if it's 0 weeks in. But add these 30 over time, what do you get? Let's solve this algebraically. Solve for W the way that we did up above. Subtract 45 from both sides to get the variable term by itself here. I will only have 30 times W, some number times 30 equals 180. And listen, this is this kind of thing that you would probably do logically if you knew nothing about algebra and I said, what do you do, in this situation? Without a table, you would say, well, let's take away the 45 that he has to see how much more he needs to save. He needs to save $180 in addition to the 45. And then you're like, okay, how many times do I have to add 30 over that time? Let's divide it by 30 to figure out. So you're doing algebra without even knowing it in those cases. And we're going to do the exact same two things. We just have that algebraic setup to kind of help us a little bit there. So W is going to equal 6. It'll take Henry, and I forgot I still have to do another problem down here. It'll take Henry 6 weeks to buy that new pair of sunglasses. I'll just put 6 weeks. But I do need that unit right there to talk about it. And I also mentioned W's number of weeks right there. So define your variable. You can use X whenever you want. You can use things that start with the word, the initial for the word whenever you want, that kind of thing. As long as you define it, you know what the units are represented in, and it makes sense to you when you write the equation. Okay, last one, number 2. Bob's sister is 6 years older than twice Bob's age. The sum of their ages is 42. How old is Bob? And then a period. This is me typing it, so it's my own typo. Bob's sister is 6 years older than twice Bob's age. Oh, that's a lot of things to say. And here's the thing about Bob's sister. I don't want to put an S for his sister, and I'm not going to give her a name, so I'm going to give her X. I don't know. Well, actually, hold on a second. Yeah, that's fine. I'm going to let X equal Bob's sister's age. So Bob's sister, I'm just going to write this again. Bob's sister is X years old. X. Bob is a different amount of years old here. He is 6 years. Bob's sister. Oh my gosh, I cannot do this right. Bob's sister. Okay, you know what? I did this wrong. I did this backwards. Whenever I hear that, I'm thinking Bob, da-da-da-da. Let's do that again. Let's do Bob. Let's do Bob's age. Bob is B years old. Perfect. Bob is B years old. Bob's sister, however, is 6 years older. It's not 6 years older than Bob's age, but let's say it was. Let's say Bob's sister was 6 years older than him. If Bob is 10 years old, Bob's sister is 16. 10 plus 6, right? If Bob is B years old, then you add 6 to it. 6 years older like that. Now, she's 6 years older than twice his age. What's 6 years older than twice 10? You do twice 10, which is 2 times 10, which is 20, and then add 6. You take Bob's age and double it, and then add 6 to it. The previous skill was something like this where you would have seen this kind of thing before. 6 more than twice a number. Something like that. Now, why did I write this like this? Why didn't I give her a variable, which I was originally going to because I was going to compare Bob to her. I need to compare her to Bob. I want to write this with 1 because I still need to solve an equation with this. We need to figure out how old they are. And I know you're like, well, give me X. But to solve a variable, we need, to solve an equation, you only need 1 variable in it, right, to get it all by itself. I couldn't use some X and be able to solve that thing. So I'm going to only use Bob's age to work this thing out, but Bob's sister is represented with this expression right here. That is an expression for her age, if she was 26 and he's 10, something like that. Now, the sum of their ages is 42. If I add Bob's age with his sister's age, I get an overall total sum, which is 42. So let's add Bob's age, B, with Bob's sister's age represented in terms of Bob's age, 2B plus 6, and I get 42 from both of them. So how old And you know what? They don't say how old are both. They just say how old is Bob. I don't even need to figure out how old his sister is, though I will figure it out for you. Let's do what we did before. We have an expression on this side that is not yet simplified. I have 1b plus 2b. I can make 3b. Let's subtract 6 from both sides. I'm going to go a little bit faster now that you've seen a couple of these. Let's subtract 6 from both sides to help solve for b. In that case there. 3 times b, 3 times Bob's age, apparently is 36. How old is Bob? You divide by 3 now. 36 divided by 3 is 12. Bob is 12 years old. Generally, you'd want to say it as a whole sentence. Bob is 12 years old. Kind of ran out of room there. How old's Bob's sister then? You can do this one of two ways. One way is, hey, she's 6 years older than twice Bob's age. Bob is 12. Do twice that, 24. Add 6. His sister's 30. How else could have you done it? Their ages add to 42. Bob is 12 plus unknown sister's age equals 42. Subtract 12. His sister's age is 30, right? So there are two different ways you could come up with it afterward. So that's some of the skill stuff we were doing, guys, and we still are doing. We're going to continue doing here on out. And like I said, this was a long, I was going to make a 10-minute video, and then I decided, as I was talking, I was like, I really want to talk about this for my kiddos who have a lot of trouble coming up with this stuff here. But even in 40 minutes, 41 minutes, whatever, all ends well. We got these all perfect the way that we needed to. I hope this made sense. That ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for tuning in here. And hey, take care. I will see you in the next one.